Hello everyone. In this lecture we will take a look at another important aspect in machine learning, which is the decomposition of the error that a predictive model makes into a bias component and into a variance component. And I will show you how you can exploit that understanding to make more accurate predictive models. But before we go into this, I'd like to refresh your memory about an early machine learning algorithm, the decision tree algorithm that you should have seen in one of the previous courses. So in order to do that, let's look at this classical machine learning data set. So this is the famous iris data set. So there's three types of iris flowers here, right? So three different species, right? And so we would like to have a model that can differentiate between these three different species. And so the features that are used are computed from what is known as the sepal and the petal that we have here, right? And so we will have two measurements for each. I'm showing you that in the next slide here. So this is the famous data set. You can see it's a very early data set. So you can see here we have these three classes, three types of iris flowers, and we have four features. So for the sepal and for the petal, we have both the length and the width measurements. Okay. And so, as you probably remember, decision tree looked a bit like a tree. So it had this root node and it goes down all the way to the leaf nodes, right? So a decision is made by propagating through this decision-making tree in order to end up somewhere in a leaf where a final decision or a final classification is made. So the dataset consists of 50 data points for each class. So you can see that here in the root node we have 50 data points in each class. And so for this constructed decision tree, what would happen is that you would have this feature x2, right? And so it would be tested with some value. If this value for x2 is smaller than this threshold value, we go here. So we already end up in a leaf. And if it is bigger, right, then we go here. Okay, and so here you can see that all our data points in this particular class here have a value for feature 2 smaller than this threshold. So we end up here where we have only 50 data points in one of the classes and 0 in the other classes. So if we end up here, it's a very clear-cut prediction that we make, right? We predict this first class. Okay. So here we have a different situation. Okay, so we still have 50 in one class, 50 in the other class. So we're going to continue with making decisions. So in this case, we're going to test feature x3 based on this threshold. So if this is true, we go here. If this is false, we go here. And so you can, for instance, see here that we now have a nice situation where there's 45 in the third class and only 1 in the second class and 0 in the first class, but we want to go as deep as possible with this tree. So here we do another split and then we have a leaf here, right? We cannot split this any further. There's a nice leaf. And here we can still keep on splitting until we end up here, okay? So this is how we make decisions given a certain feature vector. And so given in this case measurement for these four features, we can make a decision to which class this iris flower belongs to. So how is this tree fitted on the data? So this would be the representation. So just like we had linear models and sigmoid models, this would be the model representation, a tree representation for decision trees. Okay, so there's again some model parameters, which in this case would be which features to test, right? And which thresholds to test with. Okay, and so in order to fit those parameters to the data set, we make use of something called the entropy, right? So the entropy is some measure of disorder of a system. So in this case, we will compute the entropy of a set of probabilities, right? So we have here 3 probabilities, 1 for each class, okay? And that's of course reflected in the number of data points we have in each class, okay? And so we can assign a probability, an entropy to these 3 probabilities, right? And so the formula for this entropy is given here. So we have here C would be 3, right? And so we would range over those 3 probabilities and we would sum the probability times the log of that probability, Okay, so if we would have only two probabilities, let's consider that case. So we have a two-class classification problem. Then we can plot this entropy as the red curve that we have here. Okay, you can see it's symmetrical. So if we take one of those probabilities, let's say it is 0.8, right, then we know that the other probability is going to be 0.2. And since this is a symmetrical curve, we will end up with the same value for our entropy. Okay, so let's say 0.8. Now we can see that we have like an entropy slightly above 0.6. Okay, if we would have probability 0.5, so both of these probabilities would be 0.5. So that means that we should split further, right? That means that there is a lot of uncertainty about the class of that data point. And so we can see also that in that case, the entropy is maximum, right? If one of those probabilities is 1, which means the other one would be 0, right? Then we have a 0 entropy, right? So which is the one we would like to have. So we want to minimize the entropy of these nodes, okay? And so to minimize this entropy of these nodes, what you do is you start off with the root node, of course, and then you have to decide on this test, okay? And so the way you decide on this test is by checking a whole range of tests, right? So you check all the features with a certain number of thresholds, right? For each of those, you compute the entropy here, so that would be one time, but you compute the entropy for the split as well. So in this case, you would compute the entropy here and compute the entropy here, okay? Then you would average these two entropies, okay? And then you would see how much less entropy have I gained by going from this node to the next level, right? Because of course I want to have, each time I go down one level, I want to get to the minimal entropy. So I want to minimize this entropy that we have. And so you can see here, it's not entropy, it's actually the Gini index that's been used. That's more often used these days for decision trees. And so you can see the Gini index function. So that's what you see here, okay? And so plotted is that's the green line. And so that's very similar to the entropy function, okay? But it has the advantage that it doesn't contain a logarithm. And so computationally, if you have to do these tests millions and millions of times to construct such a tree, the logarithm is quite an expensive operation in a computer. So you can basically do this much faster than do this. So that's the only reason why people these days use Gini index instead of the entropy. As you can see, it's pretty much the same thing. So, like I was saying, we compute, in this case, the Gini here. We compute the Gini here, the Gini here. We take the average of these two Ginis, right? And we look at the difference. So we want to have a big reduction in average Gini, okay? And we do that for all possible tests, and we choose the one which gives the biggest reduction in Gini. And of course, we can continue doing that, and we do continue doing that until we have Ginis of 0, right? So each of the leaf nodes will have a Gini or an entropy of 0. Okay, so that's how we construct. So again, the representation, the model representation is this tree structure, and the model parameters are these tests that we're looking for, and we're fitting these tests on the data set. And the loss function is, you could call it a loss function, is this try to reduce the entropy at each level in the tree. That's kind of the loss function that we're dealing with here. So decision trees are still very popular, mainly because, of course, you can actually see what's happening. You can look at the test, so there's some way to make an interpretation of what has been learned, right? It deals both with continuous and discrete features, so you can handle all types of features. It is also invariant to monotone transformations of the features, which means that there's no, you don't have to normalize or rescale your features if you're using these decision trees. There's also some, this is related to the ease of interpretation, there's also some inherent variable selection, so the feature importance is shown here, where important features should end up close to the root node. And also important is that these are known to have low bias. Now, this of course depends on how deep you will make them, and that's what I will show in the next slide. But in some sense, you can make them very deep, like we're doing here, which means that they can learn every possible function that needs to be learned. right? And that's what we refer to as low bias. But again, I will come back to that in a few slides. The disadvantage of such deep trees is that you have high variance. Okay, and also that we will talk about in the next slide. And that results in a potential of overfitting, right? Where we have to be very careful not to overfit a complex decision tree model on our data. So just to show you that these decision trees are still relevant, so this is a publication in Nature Biotechnology. So this is one of the main journals that we have here in biotechnology. And so the actual title is "What are decision trees?" So this is really an article on where these are used and what they actually are. So it's an article for a biologist in this case. And so they show this nice example here where they have a data set that looks something like this, right? And so you would have gene pairs of genes, and so the classification that you want to make is whether these genes interact, yes or no. Right? And so the features that they have here is like they used like expression correlation, so microarray expression values or something like that. You could look at the correlation expression between these genes. You could see whether they have a shared localization, right? Somewhere shared protein localization or something like that. Whether they have a shared function, so an annotated shared function. What is their genomic distance, so how far away they away from each other on the genome. So all these kind of features. And then of course you can make these decision trees, and as you can see, why they are popular, because you can actually see why a certain classification is being made. Okay, so now let's go to bias and variance. So as I explained, you can actually look at the error that a predictive model makes, and you can split that up in a bias component. So the error due to the bias of the learning algorithm, the error due to the variance of the learning algorithm, and then there is some irreducible error. So these are errors that are not due to variance or bias, but are just unlearnable, like noise in your dataset, mislabeled data points. Those things you can never go beyond, right? So that is irreducible. Okay, so now let's consider this bullseye here. Right? Let's say that the bullseye represents the generalization performance of a model. So let's say the accuracy of the predictions of a model. Okay, and so let's say that the more we go to the center of the bullseye, the higher the accuracy. So the better the performance of our model, and when we're in the center of the bullseye, we have absolutely 100% accuracy, and here we have like 0% accuracy. Okay, now let's consider a blue point in this bullseye. A blue point is a model fitted on a data set. Okay, and so for each bullseye, we consider the same model. Okay, and so this blue point is that model fitted on a dataset. Another blue point is the same model fitted on another dataset. Now the datasets are sampled from the same task, so you could look at these datasets as different samples from the same population, different random samples from the same population. Okay, so they will just contain different data points, but from the same task, of course. Okay, and so if we do that, so here we have 8 different data sets for the same model. If we do that, we can end up in, well, basically each one of these 3 situations. Okay, and so let's look at this situation first. So in this situation, we have a model. If we present it with different samples, so different data sets, different subsamples of the same data set, you could look at it like that as well. Okay, then we will be somewhere hitting generalization performance around the optimal generalization performance, but sometimes it's much less, sometimes it's much higher. Okay, but you can see it's somewhere centered around the actual model that we're looking for. It's just there is some variance in the actual predictions, and the variance is due to having different data samples, data sets. Okay. So we call these models, we say that they have a high variance. So the error that they make is basically due to the variance, right? And they have low bias. Low bias means in this case that they are able to find the actual optimal model, right? But depending on the data set they're fitting, they're just aiming close to it. Okay, so the other one is where we have a high bias, so it's very biased, right? But it has a low variance. So if you give it different samples of the same data set or different data sets, it will generally fit a very similar model. So you will see that these models end up very close to each other, but they all fail to actually get close to the center. So in this case, the model has such a high bias that it is just not able to fit a model that is close to what we actually want to find. So the one with the best generalization performance. Okay, so these are these high bias, low variance models. Okay, and then we have, of course, even a worse case where we have both very high bias, so the model isn't able to find the good, or to fit the data such that the generalization performance is close to the red center here. And at the same time, it's very sensitive to different samples of the data set, to different data sets, so it has high variance as well. Okay, so the situation we would like to end up in is, of course, this situation where it doesn't really matter which data set you give it, it will always find a very close to perfect fit, or very close to perfect model with very high generalization performance. Okay, so what I'm showing you here is a very famous plot in machine learning where we actually decompose the error that a predictive model makes into the bias and the variance, and of course there is also the stuff we can never learn, the irreducible error. So if we plot the error here on the y-axis, right, so this is high error, low error, and we can plot the model complexity on the x-axis. So model complexity really is has to do with the model parameters and has to do with how well it can fit or to what extent it is able to learn what needs to be learned. So a very simple example in decision trees, and that's why they are very popular learning algorithm in terms of bias and variance decomposition. So model complexity could be looked at as if we have like decision trees where we say they can only be 2 levels deep, right? So after 2 levels deep, we stop building these decision trees. So they have low complexity because they will never be very big decision trees. So they will end up somewhere here, low model complexity. On the other hand, if we make them really complex decision trees, so we let them grow until they cannot grow anymore, so we would have deep decision trees with many leaves, we would end up here with complex models, okay? And so if we plot a bias on this graph, right, then what we would see is that when the complexity increases, so the complexity of our model increases, we're going to see that the error, of course, is we're able to reduce the error, right, because we are able to learn much more. Yeah? And so the bias of our model here will decrease. So for more complex models, we will have lower bias. More complex models can learn much more, and so they have low bias. On the other hand, of course, if we have a more complex models, they will become more and more sensitive to differences in your dataset, so to subsamples of your dataset. And this is especially true, of course, for smaller datasets. Okay, and so now, when complexity increases, we can see reduction of bias, but we can see an increase of variance, right? And so depending on which data set you're getting, you will get good or bad performance, which is not really what you want. And so if you sum these two, you would get this total error curve here. And so this shows you that there is actually some point here in model complexity where your model is complex enough to learn what you want to learn, but not more complex than that, because then the variance would increase. So the message of this plot is that model complexity is the most important aspect in machine learning. What you want to have is a model that is complex enough to learn what you want to learn, but not more complex than that. And that's what this plot is showing here. So now, knowing this, what we can do is we can actually, so let's say we have this high variance model here, okay? So we have seen high variance. That means that in terms of decision trees, that we would have very deep decision trees. Very deep decision trees, very complex decision trees also have low bias, right? Because they can pretty much learn everything because they are so complex. Okay. And so what we could do here is, let's say that we do have 8 different data sets. So we can easily do that by saying, okay, I take my data set, let's say it has 1000 data points, and I'm just going to randomly subsample data sets from there. So let's say that each of those randomly subsampled data sets contains 800 data points or 700 data points. So you would have differences between the data sets that you sampled from the big data set. Okay. And so you could build these high variance, low bias models on this dataset, and you should see something like this, right? Where we're close to good performance, but depending on which dataset, you will see big differences in performance in between. So you can then do what is called bagging and just say, look, what if I just take the average of these predictions? Since I know that they are somewhat centered around the optimal solution, the best solution, if I average them, I should get closer to the center, right? And so that's the idea of bagging, right? Averaging out different predictive models. And similarly, we will look at boosting. So where bagging is a way to take a high variance model, right, and to reduce that variance to lower variance. In this case, in boosting, we take a high bias model, right? So this model isn't able to learn the center of the bullseye, and we're going to boost these what we call weak learners into strong learners so that they are able to get in there, right? And still preserving their low variance. Okay, so that's what we're going to look at, bagging and boosting, 2 very popular machine learning approaches these days. So as I explained, for bagging, we get this procedure here. So what you do is you basically sample data points from your training set to create a new training set. And there's different ways to do that. And we will look at one way to do that in the next slide. Then you fit a low bias, high variance model because we're bagging, right? So we need a low bias, high variance model. So in our case, this is a complex decision tree, right? And we fit that on this new training set. Okay. And then we repeat these steps t times. So t that we have here would be a hyperparameter of our learning algorithm. And then we would take the average of these models. So mathematically, that would look something like this. So we have our models that we here. So these are our different decision tree models fitted on different samples of the training set. And so each of these, of course, have their model parameters. And we repeat that t times, and then we take the average of those predictions. Okay, so that would be a way to back a high variance, low bias model. And as you will see, the performance of this average model here will be in many cases actually much better than the performance of the individual models. So one is the random forest. Right? So the random forest algorithm is basically an implementation of the bagging approach, right? And so what they do is so we have a train set with n data points and m features, right? So that's what we have. And so we're going to construct these t low bias, high variance decision trees. Yeah? So we do that by following the following steps. So we sample n data points. So we have a data set that contains n data points, and we're going to subsample n data points, right? But we're going to do that at random with replacement. So every time we have sampled one data point, it can be sampled again. So we put it back, and in the next round it can be sampled again, and we do that n times. Right? And so the result would be a data set that indeed contains n data points, but only about 2/3 of them will be different. So there will be many times the same data point in there, but we will have different data sets if we do this t times. Okay. And so the next thing that happens in random forest is that when we're constructing the decision tree, so at each node, when you're trying to decide on which feature should be used in this node to do a test, right? So you're not going to consider all of the features, but you're going to, so we had m features, you're going to consider h feature, where h is much smaller than m, right? So that puts some randomization into the construction of the trees, and that makes sure that if you build many trees, that these trees will be different from each other. Because of course, if we're going to average out trees that are exactly the same, we're not going to do anything, nothing will happen. So we need trees that are different from each other. We do that by creating, of course, different data sets, but we also do that by limiting the features at each step in the construction of the tree by only a small subset of these features. Okay, and then of course important here, and since we need these high variance decision trees, each tree is grown to the largest extent possible. So there is no pruning. Pruning, we've seen that in previous courses, where you would cut off some leaves to make the tree less complex, to avoid overfitting, or early stopping, where you say, for instance, that the tree cannot be larger than 2 levels or 3 levels or 4 levels, and otherwise it just stop. Okay, and so we have these 3 steps. Okay, and so as explained, step 3 ensure that the back models have low bias by learning these deep complex decision trees. Right? And so we repeat these 3 steps t times, and then of course we take the average of these t decision trees. And so here you can see an example of how bagging works in time, so by adding more decision trees. So what we would have here is, this is the data set, so we have 2 features, so sorry about the confusion, but this y here is also a feature, right? And so we have 2 classes, class A, which is the blue class, and class B, which is the red class. Right? And you can clearly see that this is not a linearly separable data set. And so we see the red points and the blue points. Okay, and so what we see here is the decision function, right, of fitting one decision tree to this data set. Okay, so the brown region here would be the region in which the decision tree model would classify a data point as being red. The blue region would be the region where the model classifies each data point as blue. Okay. So you can see, since we have a very complex decision tree, we can already make very complex decision boundary here. Okay. So now here's the case where we have 3 of those, right? And so 3 of them trained on different subsamples of this data set. And then we average them out. Okay, we don't see too much difference here. But once we start adding decision trees, right, and especially here when we have the point at 50, we can see that we're getting these more nicely fine-graded decision functions, which we expect to see for this data set. So this is the result of averaging out 50 complex and high variance decision trees. So for boosting, we are going to actually take a high bias, low variance model, right? So a model with low complexity, model which isn't able to get good generalization performance for a specific task because of the high bias, right? And we're going to reduce that bias. So in terms of boosting, this is typically referred to as taking a bunch of weak learners and turn them into a strong learner, right? And in this case, we're not going to average things out because that's what we did by bagging. We're going to make additive models, right? So a meta model, which is additive, right? And so an example of such a meta model is what is known as AdaBoost. And so that's shown here, right? So we have here our individual models. In this case, we have these high bias models, okay? And so we call these the weak learners because they have this high bias, okay? And we're going to compute or build a few of them, in this case T, right? Okay, and we're not going to average out their predictions, we're going to take a weighted sum of them, right? So it's an additive model. So how does this work? So AdaBoost is one of the more famous ways of boosting, more famous boosting algorithms. So how it works is that it assigns weight to the data point in our training set, right? And so it will iteratively build models where data points that have higher weights will be more focused on. So each model will try to focus on the data points that have high weights, okay? And so what do these weights mean? Well, I will explain you here in this slide. So what we're going to do is we're going to have two class classification problems. We're going to say that one class is -1 and the other class is +1, okay? And then we're going to start with the training, so for building the first model, in our case the first decision tree, right? We're going to start with a data set where each data point has the same weight. So the weights, we will refer to them as D. And so the subscript here is the iteration that we're doing in the boosting. So the number of trees we have already constructed. Okay, so in this case, we will be constructing the first tree. And so we assign to each training data point, we assign the same weight, in this case, just 1 over n, and we have n data point. Okay, and then we're going to construct our T trees. So what we're going to do is we're going to fit a weak classifier. So we have this high bias model. And we're going to fit that to the training set using the weights that we have here, which in this case, in the first iteration, would be equal weights for each training point. Okay. And then we're going to compute this alpha here. So that's the alpha that we have here in our final model. And so alpha will be a function of the error. Okay. And in the next slide, I will explain what this actually means. Okay. So let's say we have our alpha, which we computed from the error that this model is making. Okay. And so when we update the weights for the next model to fit, for the next training set, so the formula for updating the weights is shown here. And so what's important here is that the next weight for data point E would be the previous weight of data point E times this exponential here, right? And so what are we taking the exponential of? Well, we're looking here at the prediction, and we're looking here at the true label, right? And so since the true label can be either -1 or +1, right, we have the following situation. If our prediction is positive and our label is positive, then the product here will be positive, right? And so we would take the exponential of a negative value. And so similarly, if my prediction is negative and my label is negative, I would again have a positive value here, right? And I would take the exponential of a negative value. So that's the case where we have made the correct prediction. Right? In case we make an incorrect prediction, which means that, let's say, this is positive, this is negative, then the whole thing here becomes negative. And so this negative would make the whole thing here positive. So we take the exponential of a positive. And the same, of course, in the other direction. If this is positive and this is negative, it's also going to be negative. And then with this negation here, we would have again a positive value here. So if we make the correct prediction, we would take the exponential of a negative value. If we make a wrong prediction for that data point, we would take the exponential of a positive value. And so if you look at the exponential curve here, so here we would have the positive values, right? So we would get very big values for the exponential. And if we have negative values, we get very low, going all the way up to 0, but never touching 0 itself. So that means that if we have a wrong prediction here, right, then we will actually increase our weight significantly. So depending on how wrong our prediction is, we will increase this value for our weight, right? And if we have the correct prediction, we will decrease the value of our weight. Okay, so that means that in each iteration, we will increase the value of all the data points for which a wrong prediction was made by the model. We will decrease the weights of all the data points for which the correct prediction was made. So in the next step, right, when we go back here, right, so maybe I should mention here that this Z is just a normalization factor to make sure that the sum of all the weights in each iteration equals 1. So the most important part is, of course, this thing here. And so in each iteration, we're going to fit a data set on fit a model on a dataset with different weights, with the idea is that the model, of course, focuses on getting those data points correct and has less focus on the ones that it already was able to classify correctly. Okay, and so given that we do these t times, we will end up with this model that I've shown you previously here, this additive model, where we have a weighted sum of the predictions of our individual weak learners. And so finally, if we take a look again at this formula that we had here, so this alpha, the weight that we have here, is actually a function of the error. And so I can plot that like this. So this would be that function that computes alpha, and this would be error in that function. And so you can see here that for lower error, so the lower the error we get here, the higher the value for alpha becomes, right? And so since alpha is actually a weight for your model, so the better the performance of your model, the lower the error of your model, the higher the value of alpha will be, which makes sense because these are good models, and so we want to reward them, or we want to have them to have more impact on the final sum that we're making here. And of course, a model which has an error of 50%, so that's a very bad model, that's just not doing anything, it's just doing random predictions. It will get an alpha of 0, which means that it will just be cancelled out in this sum here, it will not be used in the sum. Okay. On the other hand, if we have an error which is close to 100%, let's say, and since we have a two-class classification problem, this is actually a good thing, because whenever it says one class, it probably actually means the other class, right? And so you could just give it a negative alpha, and just every time it makes a prediction, just take the other class and make it then just inverse that prediction. That's what's happening with this alpha here. And so if we look at that same data set that we looked at for the Bayesian example, so we have these two classes here, class A and class B, then boosting gives a whole different view on how to end up with the optimal model, right? So remember that for boosting we had these weak learners, right? So high bias learners, and in terms of decision trees, these are very small decision trees. So in this case, this is a decision tree which only has one level, so only has one test, right? So this is the blue, this is the brown. So the first tree isn't very accurate in this case, right? And so if we think about the bullseye again, this would be a blue point far away from the center of the bullseye, okay? But we're going to, by boosting these things, right? So by adding weights to the data points and making these weak models here focus on those data points which have high weights, right? We can see that when we start summing these weak learners, right, the decision boundary that is constructed becomes more and more complex. Right? And so after 50 trees here, we can start seeing very similar decision boundaries as we observed for Bayesian, but from a very different perspective. So not starting from complex model, but starting from a low complex model. Right? So now, AdaBoost is one of the first boosting algorithms that were proposed. Since then, many different types of boosting algorithms have been published. And I think gradient boosting is one of the most popular these days. It has shown very good generalization performance for a wide range of data sets, and many people use gradient boosting these days to fit complex models. And so again, gradient boosting, many types of gradient boosting algorithms exist, but I will look at the fundamentals behind gradient boosting. And so the idea is actually to fit a model and then look at the errors that the model makes, and then fit a model on the errors so that that second model learns to correct the errors made by the first model. Right? So that's the main idea behind gradient boosting. And so I'm showing you this example here in regression. I will also show you an example for classification, but it's easier to explain in terms of regression. So in gradient boosting, what we're going to do is we're going to fit a model, right, on the label. Okay, so Y. So let's say that we have these data points shown here. Okay, so this would be our data set. So we have one feature X and we have one label Y. And you can see again in green, you can see the ground truth model that generated these data points. So you can see there's no noise in these data points. Yeah. And so the first thing we do is we fit this model here. And so the blue model here would be the first model that we fitted. So remember, we're doing boosting, so we deal with low complex, weak learners, right? So this is one example here for this data set. Okay. And so next what we're going to do is we're going to look at the errors that this model makes, right? And we're going to fit another model, right, H1. So this one also has model parameters. I'm not showing them here, but of course this one has to be fitted, has its own model parameters, right? And we're going to fit it on the error. So that would be the true label minus the predicted value, right? So we're going to fit that here. So that in this case, so what we have here, so this was our first model, f of x. And so we're going to see what are the errors. So here you can see this model doesn't make any error. And so we're going to have plot the error here on the y-axis. So it has no error, so that's 0. Let's say this is 0 here. No, it is 0 actually, shown here. So you can see here it's making this small error, as you can see here, right? And so that's reflected here as well. And so also those are shifted towards 0, yeah, because of this line here. And so the same thing with these points here, they will be shifted up a little bit. And so you can see that what I'm showing here is the errors that are made by this model here. Okay, and so that would be this. And then next we fit our next model. So in this case, again, a regression tree, and we fit that to the errors, right? So that's what you can see here. Okay, and so then we have our new model, which is F2 in this case, right? And F2 is actually the sum of this model here, plus the model that has learned to correct the errors of this model here. So that would be this. Okay. Now we have a new model, which is this F2. Now we can of course repeat this because this model is also going to make errors, as you can see here. That's what we're showing here. And we can fit again these errors. And so then we have another, in this case, tree that corrects the errors of this model that we have here, which in terms actually was a model that has another model in there that corrects the errors of our first model, right? So you can see we have this chain, we will have this sum of these models, as you can see here, right? And so in order for this to work, we're going to initialize with some baseline model here. So F0 would just be a model that predicts the mean value for the label, right? And so by starting with that, we can say T0, and then we can go to T1, T2, as we have done here. And you can do that large T, so capital T times. So this is our hyperparameter that we have in boosting, the number of trees we are putting in our sum. So you can also see that eventually we're fitting the errors better and better and better. So on this website here, you can find a very nice interactive plot that shows you how this gradient boosting for regression works. In this case, for a data with two features. So we have one feature x1, one feature x2, and so we have our label here, y. You can see here the shape underneath, which is our true function, right? So that's what we're trying to model here, okay? And so we start with 0 trees, and so like I explained here, F0 would just predict the mean of my label, right? And so that would be this square that we have here. That would be our initial model, and we're going to boost that. So you can see this is a blue point far away from the bullseye. We're going to boost that towards the actual true underlying model that you can see here, okay? And so what we're going to look at here we're going to look at the errors made by this model that we have here. So you can see the errors are very big, right? You can see them in the background, and the errors are of course the same as the actual true underlying model, because this is just the mean of the label, okay? And what we're going to do here we're going to fit a regression tree, so regression model, so that's what you see here, to these errors, okay? So you can see here in this region, for instance, it's making a lot of big errors because the function is here and we're predicting here, okay? So it has fitted this model to these errors, okay? You can see that it has fitted this with a very simple, low complex model, so a decision tree of only depth 2 in this case. So we have fitted now this model to the errors, and so in gradient boosting we're now going to add up this model with this model, yes? And typically we're going to have some learning rate in there that determines how much this particular model will influence this model. So how much of this is added to this, okay? So let's say we added some. That's what you can see here. So this will be our new model, our F2, which is the sum of this model plus the sum of the model of the errors. So this model is actually correcting the errors that this model is making. Okay, you can see that happening here. Okay, so now we can continue. We can take this model. It's also making errors, right? You can see that in the background. It's not changing too much, but that's what's happening. And we're going to fit again a simple model to those errors, as you can see here, and we're going to add that to this model. Okay, and that's what we're doing here. We have here these two models added. And we can continue doing that, of course. So here we have 2 trees. We'll again have the error landscape here. So we're fitting a model to the error and we're adding it to this model. So when we reach 5 trees, this is what our model becomes to look like, right? And here we can see the errors again. They should somehow go to 0, because that's in the end what we want. We want to have all the errors to become 0. And so here we can see after 8 trees, we're getting a better and better fit by just focusing on the errors. And here we have 10 trees, and you can see that this error landscape here becomes close to 0. And so now I used very low complex trees for this, so only up until depth 2. And so if I would increase the complexity of the trees that I'm using to build, to do this gradient boosting, I would get more fine graded model. So you can see here, this is complex enough to actually fit the ground truth, right? So it's fitting very well. Now keep in mind, and this is very important in gradient boosting, that the data was actually generated from the ground truth without any noise. Okay, so there is no noise in here. And you can imagine, of course, if we can fit such complex functions and there would be noise, then maybe this would not be a good choice, because I've shown you that once we're starting to fit the noise, we're not going to perform very well on unseen external data on the test set. So that's not what we want, right? So especially in gradient boosting, it's very important. You will need a lot of regularization to keep the model complex enough to fit the data, to fit the ground underlying model, but not too complex that it starts fitting the noise. And so one very popular implementation of gradient boosting, of what I just explained to you, is XGBoost. So it's very popular among machine learning experts, actually. And so what you can see here is just a small list of all the hyperparameters that can be set. I'm not going to explain them in detail. You have some backing parameters. You also have some regularization parameters like the lambdas and the c's that I talked about. And so all of these help you make sure that the complex models that can be fitted by XGBoost, so the complex gradient boosting models that keep focusing on the error, that they don't start fitting the noise. So you can see that optimization of these hyperparameters can become quite computationally expensive. And so the website also offers a very nice example on classification. So for instance, here you have this two feature data set, two classes, the orange and the blue. And what you see here, so this is the result of 200 trees. You can see the first 30 trees here. And so this would be the initial tree, and then you would add a tree that fitted the errors of that model, and you get this, and then you continue. So you can see that each of these models have very low complexity. Each of them fitted on the errors that was made by the previous model. But if you take the sum of these very low complex models, you can have a very complex fit for very complex data sets, as you can see here.